In this lab practice number 5, we were gonna learn how to use the Jominy test. Our objective for this lab practice was to carry out the standard tempering test by quenching the sample, and in a Jominy, with the Jominy test, that is a way that we're gonna use in order to experimentally measure the hardenability of the carbon and low alloy steel samples. And with this, we were gonna apply it to the results in order to make it the design of heat and tempering treatments. Also, as an objective for us, it's also to make the right selection of steels for a determined application and selection of hardening conditions that lead to the last distortion of the part during the cooling and to the maximum performance in service after the tempering. So basically, we're gonna use the Jominy test in order to be able to identify which is the appropriate way in order to make a posterior treatment for the type of part that we selected, in this case for the Jominy test. For this lab practice, we used some bars, a Jominy carbon steel. In our case, it was an 8620. Also as equipment, we use the Jominy device, a muffle, also some tweezers, the protective equipment for the muffle, and also the Rockwell hardness test, and the surface grinding machine. Finally, we also use some vernier pickers, the weighting machine, and other tools in order to make us to help us do this lab practice.
After putting our material into the oven, we made sure that it was there for a long period of time, approximately 1 hour. So the complete part of our material was 100% austenite, because it was at a higher point of the austenitic line in the diagram. So for this reason, we took the material out of the oven. We put it in a special machine where you do the Jominy test. What it basically does is that it grabs your piece of metal and it squirts some water into the bottom part, so you have a faster quenching rate in the bottom, and it goes decreasing as it goes up. What this does is that at the bottom part of your material you get martensite, then as you go up you have bainite, and then you have perlite. After that, we took our material to the mill. In the mill, what we did was we did some lines so we could take out all the surrounding of our material, and we could apply some Rockwell tests directly to our material that had already been treated. After this, we did the Rockwell tests. It was every 1/16 of an inch for 2 inches. So we had 32 tests of Rockwell, and then what we did was we plotted it in a graph. In one axis we had the Jominy test, and in the other axis we had the distance from the bottom part to the top part. So in this way we're gonna see how the variation of the toughness of our material is. In theory, what should happen is that when the water hits the Jominy tester in the bottom, it should cool quicker than the rest of our metal bar. For this reason, at the bottom part we should have martensite, which is going to be the hardest, then we're going to have bainite, and then we're going to have perlite. Those materials are more ductile and are not as strong and as hard as martensite. For this reason, we think that the bottom part of our bar is going to be the hardest one, and the top one is going to be the softer one, or the more ductile. Of course, we know that in the laboratory there's a lot of things in the surroundings that we cannot control. So for this reason, we expect some variations in our results. Here we can see what the Jominy tester looked like. how I explained, this is the piece of metal that was given to us. We put the complete piece of metal into the oven, and after it heated, we put it in the Jominy tester. This is the water squirt I was talking about, and it hits the bottom part of the Jominy tester. So this part, in theory, should have a higher quenching rate because it got colder faster than this part that is further away from the water squirt. For this reason, here it's very likely to find martensite, then we're gonna have bainite, and then we're gonna have perlite. This is the line that we did for the testing, where we did the milling and then we did the Rockwell testis.
The hardenability in steels is a measure of the penetration of hardness induced in a temper as a result of the formation of a martensitic structure. The hardenability depends on the severing of the quenching, the section of the part, the chemical composition, and the grain size of our material.
Well, the ASTM to determine the hardenability of the steels is the A25502. That is to determine the hardenability between these two methods. That is the quench test, that is the Jominy test, and the hardenability by the chemical composition.
The severity of temper, it's the capacity of it designate the letter H, and it refers to the capacity of the medium to absorb the heat in the less time possible. In this practice, there are some topics that it is really important to know. First of all, is the critical radius. Ideal critical radius is the diameter of a steel bar cooled in an infinite temperature, and it forms 50% of martensite in the center. Then the real critical radius, that is the diameter of a steel bar, and it's whatever temperature, and it forms 50% of martensite. Then the perfect temple is the temple that you have an instant cooling and 50% of martensite. You make your material resistant, but you don't have ductility, low ductility, and low toughness. Then we have the correct temple, that is to keep the temperature, the right temperature, and we have a rule that is in the material with less carbon, you have to increase the temperature.
Then to determine the ideal critical radius for our steel, you have to check the amount of carbon that we have. In our case, we have a 20% carbon, and then we have to check the ideal Jominy diameter, and in our case it was 7 degrees with 20% of carbon, and then we can check the ideal diameter. First of all, I want to explain what is the cooling rate, and the cooling rate is the amount of degrees that can increase or decrease in respect with the time, and in the Jominy test is basically the amount of degrees that goes down in respect with the distance. Well, during this practice we can tell in the tables and that the cooling rate of our practice was 10 degrees Fahrenheit over a second, and this will determine the amount of degrees that will go down in respect of the time depending of the diameter of our probe.
One important thing in our process is the austenite present in our material and the grain size of the austenite, because when the grain size increase in our material, it increase also the hardenability. So when we have a smaller grain size, we have lower hardenability, and if we have bigger grain size, we have higher hardenability. It's because the grain boundary area is being reduced. It's really important to remember that the
hardenability is the capacity of our process to produce martensite in our material. So if we got austenite, we have better capacity to produce martensite because of the also the grain size. When we were talking about the variables, also the amount of carbon in our material, it increases the hardenability. So if we have to say which type of steel it's have better hardenability, it's the one that have more carbon amount. But we have to remember that if we have a lot of carbon in our material becomes brittle. So we have to take care the amount to not be too much and not too low amount of carbon. Jominy test is a really important practice for mechanical engineers because we see and we learn how our material behavior, and when we in a period of time when we quench it. It's really interesting when we take out of the furnace our piece of metal and then put it in the Jominy tester, how at the bottom or the beginning of the piece of metal the cool down is instantaneously. Then it took a few minutes till our material already cool. The most interesting part and the most important part of this for me is when we did the Rockwell hardness test, and we see how the hardness of our material change at the bottom to the other side of the material. So we conclude that if you got a quicker quenching, you got harder materials, and if you make a slower quenching, you got soft. It because of the phases that we create in our material, and also we have to take this when we want to use a material in one application, because it's so important which quenching procedure we have to use, temperature and cooling rate.
In conclusion, we saw that it is very different how the theory of an experiment is compared to what really happens. We have a lot of variations that we cannot control. So for this reason, it increases the interest in this lab experiment, because you don't know what to expect. You kind of have an idea of what has to happen, but for example, if the Rockwell moves a little bit when you're testing it, or it's if the Rockwell indenter moves a little bit when you're doing the test, or the piece of metal rotates a little bit, you're gonna get different results that are not the ones that you were expecting. So for this reason, I think that it's very interesting, first of all, to see the different hardness of our metal, and also because we were getting very interesting results.
In conclusion, we can say that the Jominy test is it's a very important type of test for the mechanical engineer, because it let us know the different quenching rates and quenching times that different materials can have, and it's very interesting because we can appreciate this segment in which the variation of a material's phase is present. So we have all the phases through here, so it's really interesting. I found it really useful because you can determine the different hardness, as we did with the Rockwell hardness test, and it's very useful, this type of procedure, this type of test, and I think it will be beneficial for us in the professional life when we are trying to get to new different materials and get to the best phase or best properties of a material.
Jominy test is a really interesting procedure, because with this we learn that the cooling rate is really important in our quench process, because with this depends the phase that we want to create, and also the application that we want to give to our material.